Check it out now, y'all.
NanoHub U, online instruction.
In this lecture, we want to look at the relativistic velocity transformations that are a result of the Lorentz-Einstein transformations between different reference frames. And we like to work out a few examples. So most of the mathematics is pretty simple. The examples we're gonna work out are gonna basically show you how these velocity transformations work. And we'll try to illustrate some of the surprising results that are achieved when you work through these transformations. So to set up the problem, this is our standard arrangement. We have two reference frames. One reference frame S prime is moving at a velocity v sub f relative to this reference frame S. Both observers in reference frame S prime and reference frame S see an object that's moving, and the observer in reference frame S prime measures the velocity component. So he basically measures u prime of this moving object using the rulers and the coordinate system that he sets up. And the question is, if the observer in reference frame S measures the same moving object, what would he conclude about the velocity of that object using the rulers that are set up in his particular reference frame? So the issue is, how do the velocities transform from S prime to S using relativistic transformation ideas? Well, the discussion has to start with the Lorentz-Einstein transformation. That's these set of equations here, right? And to calculate velocities, it becomes very useful to take the differentials of the Lorentz-Einstein transformation equations. And when we take the differentials, we get equations that look like this. So this is probably the last time this semester we're going to write down these transformation equations, and I just wanted to pause and comment that these are really remarkable results, because, for instance, if you look at the time equation, right? If you measure a time interval delta t in the primed reference frame, the equivalent time interval in the unprimed reference frame depends on the location, the coordinate where delta t prime is measured, and it also depends on the reference frame that S prime is moving with respect to S. So what this equation is telling you, remarkably, is that a time interval depends on position and velocity, and especially when you're moving at speeds close to that of light. So this, of course, is very counterintuitive, and a lot of these results that we've been talking about for the past 2 weeks or so basically come back to this fact that time depends on position and velocity. And the results that we're going to get for the velocity transformation are no different from the results that we obtained for coordinate transformations and time transformations, right? They're going to depend on position. The velocities are going to depend on position and velocity in a way that's governed by these sets of equations. So just a comment to make sure that you understand the significance of these transformation equations. We write them down and we start to just deal with them an awful lot, but sometimes it helps to step back and think about what they're trying to tell you. So in terms of velocities, what we like to do is we like to calculate the x, the y, and the z component of the velocities that the observer in frame S measures for this object, knowing the position, knowing the velocity components ux prime, uy prime, and uz prime that the observer in S prime measures. And so to calculate the x component of the velocity, we take these differential equations here, we take these differentials here, and just form what the velocity would be in the unprimed frame. It would be dx divided by dt. We can relate that to the measurements that are performed by the observer in the primed reference frame, because we've got expressions for dx in terms of the prime coordinates. We've got an expression for dt in terms of the prime coordinates. And with a few lines of algebra, right, we then end up with this velocity transformation that says if you tell me the component of the velocity that the observer in the prime frame measures, and that's u sub x prime, and if that prime frame is moving at a velocity v sub f with respect to the unprimed reference s, then the velocity in the x direction that the observer in the s frame measures is just going to be given by this ratio. So, or by this expression, right? So this is often rewritten in the standard geometry where the coordinate axes x and x prime are aligned, right? This is often written in many of the textbooks as in this form where it says u, the velocity of an object in the unprimed reference frame is equal to u prime, the velocity of the object in the moving reference frame, plus the velocity v sub f, which is the velocity that frame s prime is moving with respect to s. Right? So that's how the x component of the velocity transforms. The y and the z components of the velocity can be calculated by taking the derivative or the differentials dy and dividing it by the differential dt, right? So we have expressions for dy. The coordinate doesn't change in a direction perpendicular to motion. So dy is equal to dy prime. The time coordinate will change according to the Lorentz-Einstein transformation equation. If you just follow the arithmetic through, what you find is that the velocity in the primed reference frame in the y direction is equal to the velocity u sub y. This is the component of the velocity in the unprimed reference frame, and that component is measured in the y direction, right? Those two quantities are related by equations that look like this. So the main difference here is that this factor gamma that canceled when we did the calculation for u sub x, that doesn't cancel here, right? That persists and gives rise to different forms of the velocity transformation for the y component. The velocity transformation for the z component is also worked out here, and you get an expression that's very similar to that for the y component. So you can see all you're doing is replacing u sub z prime for u sub y prime in the numerator. You're replacing u sub z for u sub y, and you've got very, very complementary expressions. So that's how velocities transform back and forth between the two reference frames. And so what I like to do is I like to really illustrate this by doing a simple calculation, right? And make sure that you understand the implications of these transformation equations. So to set the problem up, here's our reference frame S prime. It's moving at a velocity v sub f with respect to reference frame S. There's a moving object which is measured by the observer in the primed reference frame. And let's say this moving object, just to give some numbers, has a velocity of 0.2 c in the x prime direction, and it has a velocity of 0.6 c in the y prime direction. So I specify the velocity components in terms of unit vectors I prime and j prime, right? The magnitude of the velocity that would be measured by the observer in the S prime reference frame using his yardsticks and meter sticks and clocks, right? The magnitude of that velocity would just be the sum of the squares of the two components. So the observer in the S prime frame would measure a velocity of 0.632 times the speed of light, and he would see this object moving at an angle theta prime, which is 70 degrees. So he would see, let's call it a launch angle to make the discussion simple. He would see a launch angle of 70 degrees of this object moving as he flies by at a velocity v sub f. Now, what would the observer S measure, right? Well, the observer S would have to calculate the velocity transformation of the components of u sub x prime and u sub y prime using the equations that we've already derived in the previous slide. And so the answer is going to clearly depend on the velocity of the reference frame S prime. So what I've done is I've just taken those equations at the bottom of the previous slide. So I've just taken the equation for u sub x and the equation for u sub y, and I've evaluated these expressions using ux prime and uy prime is given up here, 0.2 and 0.6 c, and then I've just considered different values for v sub f over c, right? So I've done the calculation for many values of v sub f over c, so you can see what this observer is going to measure as v sub f increases and approaches the speed of light. And so the result of that calculation, I just plot on this graph. I plot the components u sub x and u sub y that the observer in the unprimed reference frame would measure. When v sub f over c is equal to 0, he measures exactly what the observer does in the primed reference frame. He gets 0.2 times the speed of light in the x direction. He gets 0.6 times the speed of light in the y direction. But as v sub f over c increases, right, what you find is that these velocity components are modified accordingly. And in particular, what you will find is that u sub x approaches the speed of light as v sub f over c gets closer and closer to 1. And you'll also find that u sub y decreases and approaches 0 as v sub f over c gets closer to 1. So this is remarkable because, right, not only do the values of ux and uy change, but the ratio of u sub x to u sub y is going to define the angle theta that the observer measures in the unprimed reference frame. And so this is basically telling you that the apparent angle that the observer measures in the unprimed reference frame is going to be completely different than the angle that the observer in the primed reference frame measures. And in particular here, I point out at about 0.35 the speed of light, u sub x is equal to u sub y. When u sub x is equal to u sub y, that means the observer in S sees this object moving at a 45-degree angle, whereas the observer in the primed reference frame, of course, sees it moving at a launch angle of 70 degrees. So just different results. I explore that a little bit more. Where here I just plot the angle with respect to the x-axis that the observer in the unprimed reference frame measures. So this would be the launch angle is measured in S. You can see it starts off at 70 degrees, and as v sub f over c gets faster and faster, right, the launch angle observed in the unprimed reference frame approaches 0, right? So it's in the limit when v sub f over c is very, very close to the speed of light, the observer in the primed reference frame would see the object moving in a horizontal direction. And the other thing I can do is I can calculate the magnitude of the velocity measured in the unprimed reference frame. It's just u sub x squared plus u sub y squared, and I know u sub x and u sub y from this plot, right? So I can take u sub x squared plus u sub y squared, I take the square root of that quantity, and that's what I plot here. It's the magnitude of u measured by an observer in S for this object as v sub f over c increases towards unity. So, you know, again, when v sub f over c is equal to 0, that means both reference frames are at rest with respect to one another. The observer in S measures exactly the same magnitude for the velocity that the observer does in S prime, but as the velocity of the frame increases, so does the magnitude of the velocity that the observer in S would measure. So these are just standard results, and in order to demonstrate understanding of this topic, what you have to be able to do is you have to be able to take a problem and then evaluate it and calculate different components of the velocity depending on which reference frame you're in. The second example I'd like to give is I think reverse the transformation. So in this case, I'm going to say the observer in the unprimed reference frame measures a moving object. He measures the moving object moving at a velocity of 0.6 times the speed of light. He measures the launch angle of 30 degrees for that particular object. In this case, it's this red rocket ship here that's moving at 30 degrees with respect to this unprimed reference frame. And then we're just going to simply ask, what would an observer in a frame S prime measure if the frame S prime has a velocity of 0.5 the speed of light with respect to the unprimed reference frame? So in this case, what we have to do is we have to use the inverse transforms. Those inverse transforms are written down in the bottom of this slide, right? So you follow the same argument. You flip the primes and reverse v sub f, reverse the sign of v sub f to get the inverse transform, right? What you can then do is you can calculate the tangent of theta prime, which would be the angle that the observer in the frame S prime would measure. To calculate the tangent of theta prime, you need u sub y prime and u sub x prime. You have to take a ratio. I just worked through the numbers. We're going to know what the angle is because we know theta in the unprimed frame is 30 degrees. So we got to know the cosine of 30 and the sine of 30. Those things come in. We also have to calculate gamma. So gamma for a frame moving at the speed of light, or at half the speed of light, gamma is about 1.115. So that factors in. And what I get when I work through these numbers, you can check them. I get an angle of 85.7 degrees. So that means the observer in the S prime frame sees this object moving at an 85.7 degree angle with respect to his X prime axis, whereas the observer in the S frame sees an angle of 30 degrees. I also can calculate the magnitude of the velocity that the observer in the S prime frame measures. And I won't go through the arithmetic here. It's pretty straightforward. You just have to take the sum of the squares of the velocity components in the primed frame. And then at the end of the day, you have to take a square root of that. What I get from this calculation is that u prime is equal to 0.35 times the speed of light. So to recap, this observer sees this object moving at 0.35 times the speed of light. He sees this object moving at an 85.7 degree angle. This observer in the reference frame S measures the object at moving at 0.6 the speed of light. He sees a launch angle of 30 degrees. Who's correct? They both are, because there's no standard reference frame to compare the measurements. Right? The measurements of velocity, just like position and time, depend on the relative velocity of the reference frame that you make the measurement in. So there's a standard type of problem in special relativity, which is referred to as the velocity addition problem, and I'd like to discuss that and try to give you a few examples. This velocity addition problem is usually restricted to motion in the x direction only. So that means the object that's being observed is moving in the x direction, as is the reference frame S prime. S prime is moving in the x direction also. And again, the premise is that the observer in S prime has a set of rulers and the clocks that he uses to measure the velocity of this object, and he measures the velocity u prime. The observer in the unprimed or stationary reference frame has a set of clocks and rulers that he uses to measure the velocity of this object, and he gets the velocity u. And the question always becomes, how is u prime related to u? Right? That's the standard premise for these problems. Now, To solve that problem, right, you can use the velocity transformation equation written in this form. I tend to get confused when I use this form of the equation, right? So I like to rewrite it in a slightly different way. I like to identify object that's moving as, I like to label that by the subscript 1. I like to label the velocity of the S prime reference frame. I like to refer to that as 2. And then the measurements made in the stationary reference frame, I like to refer to that as measurements, or as a subscript 3, right? And that then allows me to transform some of these symbols U prime and V sub f into quantities that read like U sub 1, 2. So U prime is the velocity of the object U measured from the reference frame 2. So the object is subscripted by the index 1. The reference frame is subscripted by the index 2. So U prime now becomes this quantity U sub 1, 2. Likewise, V sub f is the velocity of this reference frame measured with respect to this observer, which has got the subscript 3. So the velocity V sub f is given as V sub 2, 3. So that's the velocity of reference frame 2 measured with respect to observer 3, right? And using this notation, it's you can rewrite this velocity transformation equation. You can rewrite that in a much more transparent form, and it just says that U sub 1, 3 is equal to U1, 2 plus V2, 3 plus this denominator. And to me, this formulation of the problem is much easier to remember, and it's much clearer to identify which velocities refer to which. But that's just a personal preference. It just depends on whether you can keep all the symbols straight in this equation, or whether you need this subscripted notation to help you keep things straight. The virtue of the subscripted notation is that once you label which object is 1, which object is 2, and which object is 3, then it becomes very easy to sort out what you have to solve for when you do these velocity addition problems. So in this slide, I just do the transformation with this newer notation. So these are the velocity transformation equations we've already written down. I just rewrite them in terms of the subscripts 1, 2, and 3 over here, just to make sure there's no confusion. And of course, what I like to do is I like to work out some typical examples to show you how these velocities transform. So let me just do example A, and then I've got 2 other examples that you can work through in the lecture notes. But the situation is this: we've got a fixed observer. This fixed observer sees 2 things, right? He sees a green rocket ship moving at 0.552 times the speed of light. He sees a red rocket ship moving at 0.606 times the speed of light. So these measurements of these velocities he makes using clocks and the ruler in his fixed reference frame. And the question we want to ask is, what velocity would the observer in the green rocket attribute to this red object? So what is the speed of the red ship with respect to the green ship, right? So to me, I label these objects by 1, 2, and 3. 3 is always the reference for the fixed observer. 1 is always the reference for the object that's moving, and then 2 is the velocity of the reference frame of this observer with respect to the fixed one. So this is the equation that tells how the velocities transform. What we really want to solve for here is we want to solve for U1, 2, right? We want the velocity of object 1 with respect to observer 2, right? And we're given the velocity of object 1 with respect to observer 3, velocity of object 2 with respect to observer 3. So what we have to do is we have to solve this equation for U12. Well, that takes a few lines of algebra, right? You get this equation, you can put in the various numbers, and what you find out is that the red object, if its velocity was measured by the observer in reference frame 2, the object would be moving at 0.08 times the speed of light, right? So these transformation equations for velocity all have a common feature. That common feature is the numerator is always what you would expect based on the Galilean transformation. So what you would expect here is just the straight difference in velocity between these two quantities, right? That's always what appears in the numerator. The denominator is always a correction factor, and this correction factor then allows you to get the correct answer based on the Lorentz-Einstein transformation equation. So I'm running a little bit out of time on this lecture. I've got 2 more examples that I hope you'll look through. They're examples based on this identical problem, but looked at in different ways, and you just sort through these equations and solve for the parameters of interest. The mathematics is pretty straightforward. Once you make the appropriate identification of velocities, then it's just a very simple algebraically to evaluate what you're being asked to find. And by doing these simple problems, I guess I should say, you demonstrate some understanding of this relativistic velocity transformation concept. And so that's a way to demonstrate proficiency in this particular topic. So you have to think about these problems a little bit and work through a few examples in order to gain some confidence. There are dozens and dozens and dozens of examples on the web. So my advice is to go out and look at a couple of those examples and make sure you know how to use these velocity transformations to answer the questions that are being asked. So that's all I wanted to say in this lecture. In the next lecture, we're going to talk about relativistic momentum. Okay, we want to look and see if how the equation for momentum must be transformed when velocities of objects are moving close to the speed of light. So it's a very interesting lecture. The results, again, are somewhat surprising. So we'll see you when you have time to listen to that lecture. So thanks a lot.